start with saying that I'm really happy to give this course. I'm really happy because I think that group theory is very essential. And the reason why it's so essential is that it's so important for physics. And the reason for that is that it's so powerful. So I will start with asking the question, why do we have group theory at all? Why are we interested in group theory? Of course, this part will be about Lie groups. So I will then move on to the question, why do we have Lie groups? Lie groups are roughly continuous groups. And associated with those continuous groups, there will be Lie algebras. So we're going to spend quite some time studying Lie algebras, because from those one can retrieve important properties of the group. So I will go through some formal definitions of Lie algebra stuff today, and then I will, I should say as well that I should go through the matrix groups. So matrix groups are the most important groups in physics. So we will use them pretty much all the time for this part of the course. And today we're going to go some way along the path. And so we're going to study the groups SO2 and SO3. So that is rotation in 2- and 3-dimensional space. I can say now also that I'm now equipped with a somewhat bigger screen. So when I'm looking that way, it's because I'm looking at the screen, other screen. So it would be really nice if some of you could have your cameras on, because then I can get some sort of feedback for how the material that I present is perceived. It's a bit nicer to talk to people than to talk to an empty screen. So if you could turn your cameras on, thanks, Sebastian. That would be much appreciated. So please follow Sebastian's example here. Okay, so then we come to the content of this course. So why do we study groups? Okay, so why are groups so important in physics? Well, it's essentially because physical laws obey a lot of symmetries. So they are invariant under certain transformations, quite a few of them. So we have translation in space, that things look the same here and here, physical laws are the same, so that's an invariance. Then we have translation in time, physical laws work the same today as they did yesterday, etc. Then we also have a Lorentz symmetry, so the physical laws are the same under boosts. And perhaps if you haven't come very far along your education, you may think of boosts as being their Lorentz transformation. But from a group theoretical perspective, we need to include rotations as well. And then in what is normally referred to as the Lorentz group, we also include space and time mirroring. However, those one can let go of and still have a group, and that would then be the SO3,1 group instead of the O3,1 group. So I will come back to those definitions soon. Okay, those of you that have taken the particle physics course, and that should be quite a few of you, you have seen that we have phase invariance in the standard model. We saw that phase invariance was associated with the electromagnetic force, and in very similar ways we saw that the group SU2 is associated with the electroweak force, but I think you're more likely to know SU2 from spin, so the spin groups of quantum mechanics. Then the strong force is described by SU3, and that is essentially a 3D version of SU2. And again, I will come back to the formal definitions today. We also have a reflection symmetry for most of the standard model content or physics content in general. So the strong force and the electromagnetic force is invariant under reflection in space and also under time reflection. But the electric force is not. So the SU2L part, those that remember, is not invariant under this. Now, if we take a look at all these examples here, we figure out that they share all of them some important properties. So they all share the property that if you apply two transformations after each other, you still get a transformation of the same kind. So for example, if I rotate with some angle alpha 1 and then with some angle alpha 2, I get back a rotation with some other angle alpha 1 plus 2. Or if I translate with some distance delta x and then some distance delta x, what I get back is a translation with some distance. And all of these symmetry operations share that property. They also have the property that they have an inverse. So the inverse of translating is translated backward, the inverse of rotating is rotating backwards, the inverse of time mirroring is mirroring time back again, etc. And furthermore, they all have the property that they are associative. So if we take one group operation, so this will of course be a group, one symmetry operation, then another one, and then another one, it does not matter if we apply them in the order G2, 3, combine first, and then G1, or G3 first, and then G1, G2, combine. This is the definition of associative. And also for each transformation symmetry that we saw, we had a unit transformation. So what's that? That's doing nothing. So rotating with angle 0, translating with delta x equal to 0. And for reflection in space or time, we would have to include the doing nothing element of things. So we would have to include the no reflection. So the reflection and the no reflection elements would then form a group. And there I somewhat jumped ahead of myself because I used this word group. But as you are taking a group theory course, I'm sure you realize that these are exactly the properties that define a group. Okay, so here we have the definition again. I think I don't need to spend so much more time going through it because you've seen it in Paddy's part and I essentially just repeated it. But we should have closure, you should stay in the group, you should have associativity, so the order doesn't matter here. You should always have an identity, and there should be an inverse for each element in the group, which is in the group. And furthermore, the group, if the group elements commute, so you can change the order of them, then the group is abelian. So much for that. So I think that was actually pretty much known to many of you. But if there was someone who had lost this connection with physics, hope you got it now. Are there any questions? Okay, good. Okay, so now to my part of this course. So I will be talking about Lie groups. So first of all, what are Lie groups and why are they important? Well, in one word or two perhaps, Lie groups are continuous groups. That's of course perhaps not a formal definition, but it's how you can think about it, and that will work perfectly. And why they are important? Well, it's the same answer as before. It's symmetries. So Lie groups are important in physics because they describe the continuous transformation. So the rotations, boost, translations, and also the gauge symmetries of the standard model. So U1, SU2, and SU3. And in essence, the Lie groups are continuous groups. And a bit more specific, this means that they should be differentiable, such that we should be able to take any group element and study sort of the vicinity around this group element. And that little vicinity around the group element will be connected to the algebra. In fact, the algebra will be a linearization around any one group element. And they have some topological properties. So the topological properties of the Lie groups comes from the identification of each element in the group with some topological space. So for example, to make this easy, if I rotate, I can describe that rotation. Let's take this pen and I rotate it. I can describe the rotation with an angle alpha. And this angle alpha can then be used to identify the group element. The point is, though, that I need a continuous set of parameters to be able to do so. And this sort of underlying topological space, so in this case, simple case, just the alpha parameter, and that is actually what's known as a mathematical manifold. I will not go into that too much because we don't really need it. But the Lie groups then can be seen as a smooth manifold, so we can differentiate there. And a manifold it's sort of a vector space, but it's a vector space that looks Euclidean on a small scale. So the alpha parameter, clearly you can think about it as a one-dimensional number, so it's clearly Euclidean. However, at large scale, there can be different topological properties. Now, you can even see it for this alpha angle. Actually, when I have rotated with an angle 2 pi, I come back to myself. I come back to where I started. So locally, it looks a lot like just a flat space. So I can even draw this picture now. I have like an angle alpha, and locally, if I'm considering an infinitesimal area around there or around there, it looks like I live in a flat space. But globally, I have another type of topology. I have the topology of a circle. So if I go around the whole 2 pi, I come back to where I started from. Okay. Okay, and now these facts that the group is differentiable, that means that we can expand it around any group element. And the fact that it's based on a locally Euclidean manifolds means that it locally looks the same everywhere. So we can actually study the group algebra, so the space tangent to every group element in a sense, around just one point. And what point do we pick then? Well, we pick the simplest point. We pick the identity element. So we will expand the group around the identity operation in all possible directions. So here it's of course just one direction, but if I can rotate in 3 dimensions, there are more directions. So I can rotate like this, or I can rotate like this. So that we will do to study the algebra, and we will expand around one, because we can as well expand around. It's easier than expand around anything else. And it's a manifold that looks locally Euclidean around any points, so that works. Okay, I will not really go on like this, in the sense of I will not spend so much time using fancy mathematical words, because we will not really need them. So we will, for almost all of what we will do, we will use matrix groups. So we can describe them by matrices. And this implies an enormous simplification. And it will also intuitively become a lot easier because you can think about matrix groups. We will find essentially that if we take E to Lie algebra, then this will be the group in a sense. It's not completely true. It's not really a complete equal sign there, but they will be intimately related. Okay, and in terms of matrix groups, one can define the concept of being a compact group as a group having the property that if you have a sequence of matrices A, M in the group, and if this sequence converges to some element T, then that T is in the group. So that's what you would expect from a compact space. And also there exists a constant such that the absolute values of all entries in this matrix A is smaller than that constant, all of them. So any questions to that? Okay.
I was just wondering quickly, Lie algebra and continuous group are exactly this, like just another name for it, or if there are continuous groups that are not Lie groups?
It's that the Lie groups have an algebra and they are continuous group, but the Lie algebra will turn out not to exactly give all the information about the groups, but since they can be different, since they are differentiable.
Yeah. But are there
you can theorize and you can find the Lie algebra.
But are there continuous groups that are not Lie groups? That is what I meant. I just formulated it badly.
I could not cook up an example where that would not be the case. If it's continuous, I can parameterize it by some parameter, and then I can differentiate in that parameter.
Okay.
Okay. So then we move on to some more meaty stuff that is for sure useful. And that's matrix Lie groups, as promised. So we will here sort of sort all the matrix Lie groups that we encounter in physics. And all of them will be subgroups of one group. And that group is the general G for general, L for linear matrix group. So it's a matrix. It's an n by n matrix, either a complex or a real matrix. And so we define the group DLNF as being all n times n matrices, either complex or real, with the determinant not equal to 0. Can someone tell me why do I require that?
I think it's to be invertible.
Yeah, exactly. Per definition of a group, it has to be invertible, and it's not invertible if the determinant is 0. So the determinant is not allowed to be 0, but otherwise it can be any matrix that is in this general linear groups. And now we will specialize. So we will restrict the set of the properties of this general linear matrix groups more and more. And first we will come to so-called special groups. So what's special about special? So special, per definition, means that the determinant is not only not equal to 0, it is equal to 1. Special, that is per definition determinant equal to 1. Otherwise, we take all group elements that we had up here. And doing so, we get the special linear. It's of course still a linear group. It was general linear there, special linear there. over n, and then some field f, again being either the complex numbers or the real numbers. And I like to try to give examples, but the first example is probably something that not so many of you have heard of. But if we take the group SL2C, so 2 times 2 complex matrix with determinant 1, this is actually pretty important for the Lorentz group, but I think that pretty much every third-year students, except possibly for some other students that I know would have missed that. Okay. Using, okay. So this was SL and C in general, and then we make another restriction. So now we take this field F to be R. So we consider real matrices, and then we consider the orthogonal groups. And actually in very many courses in group theory, the orthogonal groups would be defined like this, that the O transpose is equal to 1. That is, the O transpose is the inverse of O. Actually, there exists a more sort of inclusive definition that we will make some use of in physics, and it is the following definition. Now we take O of P and Q, and it's all matrices in GL and R with the property that G transpose is E. So what is E? Well, E is a diagonal matrix with P entries being 1 and Q entries being -1. So it is like if we squeeze in here a matrix 1, 1, 1, etc., and then a few Q's, sorry, a few -1s, -1, etc. So we have P of those and we have Q of those. And we squeeze this big matrix in here, and we require that this whole thing should instead be 1. If you're lazy and don't want to learn too much, you can ignore this stuff. But this stuff is very important. And this stuff is actually important in one special case. It is important for general and special relativity, where this thing will be the metric G mu nu. So 1 minus 1 minus 1 minus 1, I write since I'm a particle physicist. Of course, if I was dealing with gravity, I would possibly write it like this instead. That's just a convention. And in one case, I have SO 3,1, and in the other case, I have SO 1,3. But those groups have exactly the same properties. They are 1-to-1. Okay. Anyway, so to repeat, we have a pseudo orthogonal group if we leave this general thing here with this big matrix inserted, and if we ignore this matrix, we call it just an orthogonal group. And in fact, the world isn't fully consistent as well, so I have seen what we would call pseudo orthogonal groups being referred to just as orthogonal groups. There is no consistency police in the world of physics, so people use slightly different terms for the same thing. Okay. Now we can take the determinant of this defining relation. So this is something that the group should satisfy. And now if we take the determinant of this, so the determinant of the left-hand side should be the determinant of the right-hand side. Then the determinant of a group element G is the same as the determinant of the group element G transpose. So we have the determinant of G squared multiplying this thing, determinant of E, is equal to the determinant of E. Now we can, of course, just cross these out. So we are left with the constraint that the determinant of G squared should be 1. So this is something we must have for an orthogonal group. And I have jumped ahead of time, so I've already said that we have the one important group, which is property, the Lorentz group. An important group that is actually only orthogonal is rotations in three-dimensional space, or of course rotations in any number of dimensions, including 2 dimensions. Are there any questions so far on the matrix groups so far? Okay, then I move on to special orthogonal groups, and I think you can now guess what they are. So they are orthogonal groups with the determinant 1. So they are actually, yeah, they are actually the real rotations, and if I include rotations and reflections in three-dimensional space, I get O3. Possibly I was a bit sloppy there. So rotations in three-dimensional space is SO3. Then we can also, instead of requiring the matrices to be orthogonal, we can study the related concept of being unitary in the case of complex matrices. So the unit, so U, PQ, or often just U, N, because we will again not consider this, we will again take this E element to be exactly 1, and then we will have the UN instead of UN comma 0. So actually we will only use UN, not UN comma something, and not this general form either. Okay, so they are the unitary groups, if you have for complex matrices. And again, we see that from this defining relation of the group, if we take the determinant, we now have the determinant of G once and of G dagger once, so it will be the determinant of G absolute value squared, because once it's then complex conjugated, times the determinant of E, and that should be equal to the determinant of E, and then we cross these out, and we get a constraint on the determinant, namely that the absolute value of the determinant should be 1. Since the absolute value should be 1, the determinant is given by some phase. And again, we can, as we did for the orthogonal groups, we can require them to be special. Doing that with unitary groups, we get the special unitary groups. So the subgroup of unitary matrices with the determinant 1. And here again, we will actually never need anything else than 0 here in this group, sorry, in this course. And so most courses, many courses would omit this more general definition and just define those. And as an example, we have, of course, the SU2 of spin, or the SU2 left of the electric force, and the SU3 of color. Then I will make one more definition, and that is of the symplectic group. the symplectic group you're not nearly as likely to encounter, but I include it here sort of for completeness. And we define it in a similar way as we did with the orthogonal and unitary groups. But instead of leaving this diagonal matrix with ones and -1 invariants, we have a similar constraint here, but we leave this matrix invariant. And I don't, frankly, I never use them, but they do appear if one is using Hamiltonian mechanics, translating between they appear there in the context of Poisson brackets, but I would expect that you will never see it actually. Okay. Do I have any questions to this? Yeah, I think this should be fairly easy and clear. So this way we have done it here by putting constraints on the matrices, on the forms of the matrices having determinant 1, etc. This is how groups are normally defined. But actually they could be defined in an alternative way, and I will list it here just for completeness because I think it is nice. So instead of looking at the form of a matrix, we can ask ourselves, what does the matrix leave invariant? And then for unitary matrices, if V is some vector in the vector space, it will leave V dagger V invariant. For orthogonal matrices, it will leave the ordinary scalar product invariant, so V transpose V. Actually, special matrices, so the determinant condition turns out to correspond to leaving the Levi-Civita tensor with n entries for n dimensions invariant. And of course, analogous to this condition, if we have O something comma something, we have, for example, for this Lorentz group O 3,1, it leaves this 4-vector contraction invariant. That could be an alternative way of defining groups, and it's much more elegant, I think. But I don't do it this way because no one else is doing it. Well, almost no one else is doing it that way. This book points it out. Okay. Then after this, I will move to the Lie algebra. So this is another good time to stop and ask if there are any questions. If there are no questions, I will move on to Lie algebras. So first, I'd like to point out that two groups are isomorphic if the functions defining the group multiplication laws are equivalent. So, for example, the group U1, unitary 1-by-1 group, so that's just a complex space, and the group SO2, so rotations in a plane. But showing the equivalence of two multiplications law is typically a difficult task, and in general, now we are studying mainly matrices, and then the multiplication is at least linear, but in general it can be non-linear as well. So this is a hard task, and so it would be nice if one could linearize the group and find out some nice properties of the group just by linearizing them. And that is exactly what we will do. So we will find substantial part of information about the group and the original group composition and multiplication laws by linearizing the group. So since the Lie groups are continuous, they can be linearized in the neighborhood of any of its points. And we will do so by a Taylor series, so it won't be anything fancy mathematical, but a plain Taylor series. And see what we will do so, and we will see what we can learn from that. And since we have this manifold property that locally the tangent space of the manifold looks the same everywhere, we can do this in the vicinity of any element. But to be a bit more specific, if we consider a group element A, then the neighborhood around the group element A, then we can map that onto the neighborhood of a group element B by multiplying A with B inverse A. So, and of course this is an element in the group. So B inverse A, then of course the A cancels and I get just the B remaining. So I'm around B. So I can as well study the properties around B. And then of course we choose to study around 1. And then we come to this Lie algebra. So linearization of the Lie group generates a set of operators, and these elements form the Lie algebra. So the Lie algebra is constructed by linearizing, that is essentially differentiating the Lie group. And then one comes to the question if one can recover the Lie group from the Lie algebra. And that turns out actually not to be the case. Possibly one can get a hint of why this should not be the case by just thinking about the circle, the fact that it looks locally the same in every point doesn't say anything about the global structure. So globally, we will actually find that groups having the same algebra can have different global structures. Okay. So we will linearize groups, and then to get back the group, one could imagine that one makes some little infinitesimal expansion around the group element, and then exponentiate this infinitesimal expansion, and one can then ask the question, what do we get back? So we can attempt to move far away from identity by doing small group operations many times. So in other words, we take k step, many k steps, let k go to infinity. We study 1 plus 1 over k times this times whatever we get as the first order series expansion of the group. And then we raise that to the power of k. So this is how we can define an exponential of, and it's also equal to the Taylor series of that exponential. So we make this exponential map, and we see how much of the Lie group can we covered from the exponential map, so e to the Lie algebra, and the answer will be a lot. Are there any questions to that? Then I will talk about something that is very important, namely the Baker-Campbell-Hausdorff formula that you may or may not have seen before. This is or among other things at least, a matrix multiplication relation. So if we take e to a matrix A, e to a matrix B, now if e to this and e to this commuted, we could just add it and we would have e to A plus B. But in general, these group elements do not commute. And these A and B, which then live in the algebra, they do also not commute. So there is a formula relating E to A, E to B, to E to not only A plus B, but E to something. And this is the Baker-Campbell-Hausdorff formula. So it says that E to A times E to B is E to A plus B plus 1/2 commutator of A and B plus more term with nested commutators, so commutator of A commuted with commutator of A and B, etc. So that sum in the exponent goes on here. But what is very important to note is that if this commutator is an element in the algebra, and the algebra is some sort of Euclidean space, actually, some linear vector space, then this is in the algebra. But if this is in the algebra, then this is also in the algebra, etc. Also for higher order nested commutators with more brackets here. So if this commutator is in the algebra, then this whole thing is in the algebra. And that means that this thing as a whole is in the group. And this means that we can recover a lot about the group from the algebra. So this is to motivate why do we study the algebra. And of course it will turn out this commutator will be in the algebra. So that this whole thing is in the group, because it's got to be the case, because this times this, if these are group elements, should be in the group. So this better be in the group. So these commutators here better be in the algebra. Okay. So a few words about the definition of Lie algebra in as formal as I will get, I think. So let's define a Lie algebra. It is a linear vector space with a sort of vector multiplication law. Actually, this vector multiplication law in our case will be nothing but exactly the commutator between matrices. This vector multiplication or operation, or whatever you want to call it, it's called different things in different places, has the property that it doesn't take us out of the algebra. We stay in the algebra if these elements are in the algebra. It also has the property that we can form linear combinations and we're still in the algebra. So this is the vector space property. And it's a linear space, so we can take a linear combination of elements in the algebra, commute it with an element in the algebra, and we get this thing here. So it's linear in the arguments here. And interchanging the elements of a vector multiplication, we actually should retrieve minus the same thing. And of course, you know that the matrix commutator will satisfy this relation. We should also have a Jacobi identity. So this is A commuted with the commutator of B and C plus cyclic permutations. So here I read A, B, C, then I read A, B, C here, and A, B, C. So it's this thing plus cyclic permutations. That thing being 0 is the Jacobi identity, and it is completely straightforward to prove that this is true for matrices. You just multiply out this, and then you will have the result just by looking at the terms. However, this commutator is not associative in general. So this does not hold the order here, doesn't matter. And in addition to this, we demand that the Lie algebra has a finite dimensional space. So we are interested in groups that can be described by a finite number of parameters. So the Lie algebra has a finite dimension. So it comprises a set of n linearly independent elements that live in this Lie algebra. And they act as a sort of basis by which every element x of the algebra can be represented in a unique way. So this looks just like a decomposition of a vector x in a normal vector space. So nothing strange there. So in other words, the algebra consists of an n-dimensional vector space. And if the coefficients standing here in this linear combination, if they are real, we say that we have a real algebra. Then we can complexify the algebra by allowing complex coefficients there. And then we have a complexified algebra. And okay, so to conclude, we have that the Lie algebra is a vector space with an alternate product, so the order implies a swap of sign. And in this case, the alternate product will be the commutator, but in general, it's an alternating product satisfying the Jacobi identity. So it is becoming time to take the break. So I don't want to drag too much into the space of the break. So let's first see if there are any questions for the general audience. No questions. So what I will do then as well is that I will say, okay, I will not say anything important, so take a break. But if someone wants to ask me questions, I will be in front of the computer now for a few minutes, and then I will also come back, say 10 past, to see if someone has had any questions popping up during the break. So this is to simulate standing around in front of the whiteboard and answering questions. Yeah, so please take a break or ask me questions.
Excuse me, but if in the linearity of the project, if you could scroll up a bit.
Yeah, you're, yeah.
No, down when you define the Lie algebra.
Yeah.
See there. Is there an error in the linearity? Is it supposed to be alpha commutator AC? There, or is that correct?
Oh, yeah. So let's see. This looks like a typo. So it should be A here, and B there, and it should. Yeah. Of course, it should be A. It was so obvious to me that I didn't. I read it.
Yeah. No,
yeah, you're right. I will change that. Thanks.
Yes. Yeah.
And I was just wondering, for curiosity, for pseudo-orthogonal groups, when we define that, we say that this E is the metric, and you say that P should be +1 and Q should be -1. Does it also work for curved spaces? So when we don't have just the Minkowski metric there?
Well, this is the definition of the group is what it is, and that is with this E that has entries 1 and -1.
Okay.
And actually, the only example that I can come to think about is exactly the Lorentz group. So maybe it is a bit unnecessary to define it in general. Okay, so are there any more questions? If not, I will also take a break. So I'm back if there are questions. So welcome back. It is 15 past, so we should continue. I just want to say that before the break, I was led to believe that there was a typo in this equation highlighted in yellow here. The point is that it should be linear in the arguments, and it actually is linear in the arguments. So there is an alpha pulled out there, and then it's it's A commuted with C. Sorry. But A commuted with C it should be, yeah. And then beta is pulled out, and then it's B commuted with C. Okay, so there is a typo. Good. I should fix that. I'm sure there are more typos in these notes. It takes much more time than there is available to fix error-free notes. So please let me know if you find something. Maybe some questions to the material popped up during the break. If not, I will go on. So we finished off here. We said that the Lie algebra was a vector space. So you can use all your vector space intuition with some alternate product, and that is the commutator in our case. It satisfies the Jacobi identity, and that will be automatically satisfied for us because it satisfies matrices. It will probably also be one of the exercises to prove this, but it's pretty trivial. Okay. Now, due to the first condition, so this in the list of conditions, so this commutator of two basis element, that this also belongs to the algebra. We have the result that we can write the result of this commutator as a linear combination of basis vectors in the algebra. So the commutator is a linear combination of other elements in the algebra. And here I should say as well that I used the Einstein summation convention, so I'm explicitly summing over the repeated index L here. So this is a sum. And even though we have n cubed such coefficients, we have n cubed, one for n for I, n for k, and n for L, but they are not at all independent. So for example, it's supposed to be antisymmetric in I and k here. So that must be reflected also in the coefficient here. And those coefficients are called structure constants. Actually, I like to point out that the structure constants depend on the basis on which e's one are using here as basis vectors in this vector space, that is the algebra. But one will often hear the expression that they define the group. And that expression comes from the fact that if we know them all in whatever basis, then we know a lot of the properties of the group. But they are not necessarily the same. They are certainly basis dependent, and that is pretty obvious from this and the fact that this algebra is a vector space, but it's nevertheless something that people tend to forget. So pick another basis, you will have other coefficients there. But actually people tend to take roughly the same basis, modulo perhaps some factors of 2 and signs. Okay, also, however, given a set of basis elements, the structure constant specifies the Lie algebra completely, but only if the set, so the basis is given. And Lie algebra with complex structure constants, so if these here are complex, is said to be a complex itself. So in many cases that we will encounter, this will be real, and I think the example that you're most likely to be familiar with is SU2, but these will essentially be the Pauli matrices, and this will be an epsilon and the remaining third Pauli matrix. And we will actually, there is one example where we have a Lie algebra that is real for one group, but which, if we then complexify it, we get another important group. And that is an example that if we complexify the SU2 algebra of the group SU2, so the algebra is often written with small letters, whereas the group is written with large letters. So if we take this algebra and we allow complex coefficients here. So if these are essentially sigma matrices, then we have, this is essentially epsilon, then epsilon is clearly real. So we have then a real Lie algebra for SU2. But if we allow complex coefficients here, we instead span the algebra of SL2C. Okay. an important thing to note that also makes the structure constants depend on each other is that we have is that the Jacobi identity implies constraints. So if we calculate the Jacobi identity for the generators EI, EJ, and EK, which you now can think about as matrices. So the elements, basis elements in the algebra here. Then let's see what we get. So what has happened here is that we have used for this bracket here the relation up here that EI, EK, EC, IK, so this order here, L, and then EL, so a sum over L implicit here. So here we have then J, first index going there, K, second index there, summation index L appearing here. And this constant, this C is just a number, so we can pull it out of this bracket here. And the remaining structure is carried by EL, so we have that commutator there. And then we do the same logic to the other terms here. So here we then get C, K, I, and the sum over L and EL. And here we have C, I, J, and the sum over L, EL. Then we do the same thing again to get rid of this second bracket. So the first term only stands, and this is replaced by C, I, and then L, and then M, and the same M here. Similarly for the other terms, I don't think I have to iterate those steps. The point is that we get some constants all multiplying some EM here. And we sum over M here. But because all the elements EM are linearly independent, so they, as we said, they form a basis. So that means that this must be true in general, even if we divide out this guy EM here. So we thus have that these coefficients alone should equal to 0. So 0 is equal to this thing. So here we see that we get this relation for the structure constants. They must satisfy these relations. And perhaps some of you would be more familiar if I had labeled the structure constants F. They are often labeled F, so F, A, B, C, etc. And then as I said, we have the antisymmetry relation, which imposes some further constraints on them. So they are, while they are naively n-cubed, often there are much fewer that are independent. And of course, this relation here implies that they are antisymmetric in those indices, so I and K. Here IK and here IK. But actually for SUN, we will find that they are fully antisymmetric in all their indices. Okay, so I will not be more formal than I have been. I will be less formal and move on to examples. But let's first see if there are any questions to this. Okay, then I'm skipping this stuff. This is more formal definitions of a field, vector space, and an algebra for those that possibly are mathematically minded and want it, but we won't need it, and I would rather do physics, so I'm completely skipping it. And instead, I'm moving on to something which I believe is much more understandable, namely simply rotations. So for those that thought that this concept of an algebra was pretty abstract and what's the point of it, I hope that it will make some more sense once we have studied the algebra for the rotation group. So we will start with SO2 and then we will move on to SO3. Okay. So the SO2 abstract group can be represented by SO2 matrices. So one can think of SO2 as actually being some sort of abstract group, but it fits perfectly well to think about it as matrices. But you can also have representations of those matrices that do not look like ordinary SO2 matrices, so not like rotation in a plane, and of course E2 a phase is the prime example. Okay, so now you may know what a rotation matrix looks like in 2 dimensions. I hope you do, but let's assume that you don't, and then we will derive from the constraints here what it must look like. Okay, so we start with a 2 times 2 real matrix. So we write it in some general form. Then we had the S, the special, giving that the determinant should be 1. So the determinant of this matrix should be 1. Now, the determinant is given by AD minus BC here, and this should be 1. Then we have the orthogonality condition. Here is another typo, right? So it should be A transpose is A inverse. That is what we use here at least. So here we have a transpose. So I have simply swapped the position of B and C. This is a form that you may or may not remember for the inverse of a 2 by 2 matrix. It's 1 over the determinant. Now, luckily for us, the determinant is 1. So this is just 1. And then it is dA and minus B and minus C. So with this, we conclude that D, there's a 1 here, so D must be A and C must be minus B. So we have this condition and this condition from A inverse being A transpose. Now, if we insert that back into the determinant condition, so D is A, and we compare that to what we have up here, we see that we will have A square, and then C is minus B, so we see from up here that we will have B square. So A square plus B square is 1. So both A and B must be between -1 and 1. And if they should square to 1, a convenient way of labeling them is by the cos and the sine of some angle alpha. And now we're back to what I think you know from some basic course, the form of a rotation matrix. So we take our R of alpha to have this form. So A was cos and B was A, so we have cos, cos, and we have sine here and minus sine here, and the angle should be between 0 and 2 pi. So now we have derived this form. Not assumed that we have not assumed that we knew it from before. We have derived it from the constraints on this matrix. Then we note that 2-dimensional rotations commute, as you know. So this means that R of alpha, R of alpha 2, R of alpha 1 is R of alpha 1 plus 2 is R of alpha 2, now opposite order. Plus 1 is R of alpha 1 and then alpha 2. So the group is abelian. And therefore, if we were to reproduce, if we were to represent it by complex matrices, then it's complex, well, it's complex irreducible representations. So those that cannot be further block diagonalized are one-dimensional. So this way. Of course, we can cook up stupid representations of the group. We can construct a big matrix where we put lots of copies of this guy on the diagonal. That would be a perfectly viable representation. It wouldn't be very useful, but okay, we can do it. Okay. Also, we had it SO2 is then an example of a compact Lie group, because this parameter alpha is in a finite interval. So that we have it's compact. So any questions to that?
I was just wondering about the form of the rotation matrix.
The rotation matrix.
Yeah, so is this one from the looks of it, it looks like clockwise rotation because of the negative sign?
How you define it, it's just a convention. Actually, I had a minus sign in the other place last year because that was what Hugo had done, and then people thought that I didn't know the difference between a passive and an active rotation. So I thought, okay, I changed the sign this year so we avoid this problem. I would say that this is the most common form of a rotation matrix with angle alpha. But you can define it such that you're rotating the other way around. So that's not a problem. It's not particularly interesting.
Okay, so it's a difference between active and passive rotations. All right.
Yeah, well, no, I would not say so. If you want, you can view it that way, but I would say it's the matter of how you define your parameter. It doesn't have to be the difference between active and passive rotation. No.
Okay.
Okay. But this is the more common way of defining it. But you could have done it the other way around. Yeah, it's not interesting. It's just a definition. Actually, for everything that we will do, essentially, and especially when we come to the Lorentz group, you will find lots of conventions everywhere, and they are different. So it's very dangerous to take these notes and blindly take an equation from anywhere else, because it's not unlikely to be off by in particular minus sign. It could also be a factor of 2 or anything small. Okay. Okay, so that was the sort of default way of representing SO2, but as we have alluded to, we can also represent it by e to some phase. So now we will take our ordinary rotation matrix, but we will let it act on a complex space, and we will see if we can retrieve this statement that its complex irreducible representations are one-dimensional. Okay, so the statement here that I'm pulling out of a hat is that the eigenstates of R alpha are these vectors. One could of course calculate them, but that's not really the point. I'm just stating that these are eigenvectors, and so I act with them, the first one here, on my I act on it with the rotation matrix. So I get cos alpha times 1 here, I get sine alpha times I here, etc. And now if I look at this, I see that what I have standing up here is e to I alpha, and what I have standing down here, I can write it as I times e to I alpha. So I see that this guy is proportional to that guy with the constant e to the I alpha. The similarity, so the point is that this is then an eigenvector. And I can also find the eigenvalue of this eigenvector. And it will be the same thing, but with a minus sign. Oh, okay. So here is the remainder from last year. The signs there should be swapped because this is my lambda 1. It's this guy, and it ends up here with the plus. So those should be swapped. The danger of changing conventions. Yeah. Anyway, the point is that these are eigenvalues, sorry, eigenvectors with some eigenvalues. And so we can rotate to the matrix of eigenvectors instead. And the coefficients in that rotation matrix is then given by these guys sitting there. And applying then the rotation to the eigenvector basis on the rotation matrix R of alpha. So this is the matrix, and that is, and what we have standing here is the inverse of it. Then gives us some diagonal matrix. So we can confirm the statement that the complex irreducible, the complex irreducible representations are of this form. So indeed we obtain something that is block diagonal here. So what we had initially was irreducible because it could be brought to this block diagonal form. But now we are back to this smallest representation on each element here. So on this first one-dimensional space and on this one-dimensional space as well. So with what we have actually is that we have two non-equivalent representations, and with non-equivalent we mean representations that cannot be related by a similarity transformation. So that is representations that cannot be written off this form here. Okay, so what we can do then is that we can write the representation d of alpha on this complex space, so not to be allowed complex vectors, but we still have the same real rotation matrix. Then this representation on the two-dimensional space can be written as something acting on only one component and something acting on only one component, differing by the argument, also what you have in front of the angle. And then this plus here is what we use when we can reduce a matrix to block diagonal form. So hence it's a plus here. Does that make sense? I'm not entirely sure how much you have seen before. Yeah, good. Okay, and then we also had that the representation U is bijective, so it's 1-to-1. So we have obtained what I already mentioned, that SO2 is isomorphic to U1. It's essentially the same group. One would say, I'm pretty sure a mathematician would say that it is the same group, just the different representations of it. They are isomorphic. Okay, then we note that the elements of this guy here, we can view them as lying along as a circle, the unit circle in the complex plane. So actually we have found that the abstract group SO2 is isomorphic to the matrix representation SO2, is isomorphic to U1 unitary 1 times 1 matrices, and to the circle 1 dimension S1. Now, in fact, there are actually infinitely many non-equivalent representations of SO2. So the ones that we've spoken about so far have the property that you must rotate by 2 pi to get back. But actually, we can allow ourselves to have an integer k in the exponent. So this here with the k, being the new thing here in the exponent, has the property that it is a representation. And those representations here, they are called the standard irreps of SO2. So they are clearly irreducible, and they're called the standard irreps. And if you're not convinced that this is a representation, you can easily prove it. So you have to prove that it satisfies all the group properties, and all of that should be very simple. And furthermore, UNAS representations, these are non-equivalent representations representing the same group. So these up here cannot be taken to each other by a similarity transformation, so by some matrix in general, but in this case it will just be a number. Matrix X inverse, this exponential, and then S. Of course, this is a commuting group, so the S we can just pull through, and then this guy cancels against this guy, and we just have that this exponent is equal to that exponent, and that clearly only works if K1 is equal to K2. Okay, any questions to that? Okay, then we will have a look at the generator of the group SO2. Would be nice if we could get to SO3, because there it's when we get something that is a bit non-trivial. But from the discrete part of this course, you should have encountered the cyclic group Cn. So it has, that one has n element, and it has the property that you can, if you multiply with one of them, you can move around. So this would be C3, for example, and if you take the group C4 and you raise one element, first one, to the power 4, you would get back to the same position. And then you can imagine letting the number of elements in the cyclic group go to infinity. And you could imagine that you have a ring of states here. So, and then if this is continuous, we can talk about differentiating. So this is what we will do now. But if you want to connect the statement of generate from the discrete part of the course, which I think you have gone through, have you? Yeah, to the concept of generating in this part of the course, then you can think about this. But now we will do this, but we will go infinitesimal and we will differentiate. So finally, we will differentiate and see what we have in the algebra. Okay, I think I will actually take this the other way around next time I'm doing the course. Okay, so we do what we have been talking about. Finally, we get Taylor expanding. So we Taylor expand the representation near the identity. Now, recall here that our matrix was something like a cos, a sine, and a minus sign. So, so this was my R, and of course there were argument alphas to my coses and my sines. This was my R of alpha, and if I now differentiate it, the derivative, and I evaluated that alpha is equal to 0, I have that the derivative of the cos is of course the sine, and that alpha equal to 0, that is 0, so I have 0 here and I have 0 here. The derivative of sine is the cos, so it's standing there and there with the minus sign. So we concluded we get this. So this matrix X is our infinitesimal generator of rotations in 2 dimensions. So this is the guy that we should put in the exponent to generate the group. And then we can see that we actually get the same thing if we do this around another element. So here we have written out dr d alpha for a general alpha. So cos gives minus sine. Similar here, sine gives cos, and minus sine gives a minus cos. So this is what we get in general. Up here, we evaluated it for alpha equal to 0. But we see now that this matrix that we obtain here, we can actually write it as our generator, this guy here, acting on the original matrix R. So this is then our R. So this is, if we multiply these matrices together, we see that we obtain that. So this times this gives the minus sign standing here. This times that should give a cos standing there. This times that should give a minus cos standing there. And finally, this times that should give this minus sign standing here. So the point is that we get dd alpha of r of alpha is x r of alpha, which is nothing but a simple differential equation. And that simple differential equation, I'm pretty sure you know how to solve, and it gives us that r of alpha is e to alpha x, where x is then the generator, the only generator in this case. So the algebra is a one-dimensional space. And of course, if we want, we can also expand it out in this way, the definition of the E2 matrix. So we see that we have this exponential map between the group elements and the element in the algebra. So the element in the algebra, and here it's written d of x. This is to denote that we have a representation on the algebra. Just as we have a representation of the group, we have a representation of the algebra. So again, x lives in some tangent space. So the span of all tangents vector of SO2 near the identity. It doesn't actually matter if it's near the identity. So x spans the algebra, all of them. But here it's only one generator. And if we would have a look at these standard irreps that were mentioned somewhere, up here, then we see that we get down an additional factor of k. So we have this. So we can label the states by the generators if we want, or more briefly by the k's. Are there any questions to this? Okay, so then we get to something more interesting. That is the first time we actually see the structure of this. So we will get to rotations in 3 dimensions. So we will consider the group SO3. And here we repeat the formal definitions, which should be in the general linear group, and D transpose should be 1, so D transpose should be the inverse. And the determinant should be 1. Now, an important difference compared to rotations in 2 dimensions is that this is actually a non-abelian group. So here, it does matter in which order we rotate things. And this, so now actually we can take what we have learned from the 2-dimensional rotations, and we can apply it to the 3 to rotations around the x-axis, the y-axis, or the z-axis. And we will have 3 different matrices. So let's say that we're rotating around the x-axis. Then the x-axis stays the same, it doesn't change. We have some rotation matrix for the y and the z. And going back to the comment about the sign, you to have the structure constants being epsilon, you want a particular relation between the signs in these three matrices. But if you're just considering SO2, it's utterly irrelevant. And here, if you change all the signs, it's also utterly convention dependent, and now they're all particularly interesting. Okay, so in whatever direction we point, if we should get to a general direction, so make a general rotation, we need free rotation. We need to do free rotations. Here they are described by some angles, alpha, theta, and phi. Now, there are very many ways in which you can define the order how you make these. Not only if you first rotate around x and then y and then z, but also if you use extrinsic or intrinsic coordinates. So if you would use extrinsic coordinates, I would guess that's the first thing that comes to mind, and that is one is considering some fixed system with some fixed axis x, y, and z of the original coordinate system. And then do the rotations in whatever order, will give us different parametrizations. It will all represent the same group. But what is actually often done is to use intrinsic coordinates. So one can describe the rotation first by some rotation in some direction, say the x-axis, and then a rotation around the new z-axis. So you see that there are many ways of parameterizing this, and it's a bit of a mess to figure out exactly what people are doing. And so really people use very different conventions. And all of this is some sort of, in any case, it's described as Euler angles. And there is one particular parameterization, so one particular ordering, and there in which one does the rotation in one particular way and gets one particular matrix form. I don't think it's so interesting to go into the details of that actually, but what is interesting is the generators here. So now let's go back to what we had here. So we had these rotations here, and of course we can differentiate them, and again we would have some 1 and -1 on the off diagonal, and we will have 0 on the diagonal if we do it around, if we expand around the identity element. So we will get these different generators. And these different generators then span the Lie algebra. So here finally we get something that is a bit non-trivial and interesting. So now we have a three-dimensional Lie algebra, three-dimensional vector space that is spanned by these three matrices. And if you stare at the matrices, you will see that they are traceless and antisymmetric. We will see in a while that this must be true in general. They must, for all SONs, they must be antisymmetric. It will come in one of the exercises. Well, if they must be antisymmetric, it's actually pretty trivial that they are traceless, because you cannot have anything on the diagonal, because the matrix should be minus its transpose and the diagonal is mapped to itself. So we can say that the SOP algebra in this case is the real 3 times 3 matrices with the property that x transpose plus x is equal to 0. And the trace of x we can add if we want to, but it really follows from it being antisymmetric. Okay. So if we look at what we have here, we just have a bunch of 1s and -1s on the off diagonal in various places. And this means that we can actually describe the matrix element of this matrix by matrix element components JK of the matrix AI as essentially the Levi-Civita tensor. Here we have defined it with the minus sign, but that's a complete convention, which however is connected to other conventions. What I'm talking about here is that if we consider the commutator with I and Ij, and this is some linear combination C, I, J, K, A, K. Of course, if I swap the sign here and I swap the sign here, I swap it twice on this side, so nothing happens. I swap it once on this side, so I get a minus sign, which I must then absorb into this constant. So in that sense, it matters. But that constant is also defined in different ways in different sources. So in many places, there will be a minus one in front of the constant from the beginning. So it's all conventions, but they are connected to each other. So yeah. Okay. That was what I was actually talking about before when I had a question about the sign. Okay, so if we define this matrix to be minus epsilon j I k, and you can check for yourself that we need the minus sign here. So for example, we take A to be 1, so we take x here. Then we should take row 2 and component 3. So we see we end up with this minus sign. So we must have minus epsilon 1, 2, 3, because epsilon 1, 2, 3 is 1. I suppose you have seen it, but in case you haven't, here is the repetition of the definition of this Levi-Civita symbol. It is 0 if any of the two indices are the same. It is plus 1 if they are ordered like 1, 2, 3, or 3, 1, 2, because it's actually also 1, 2, 3 if I read cyclically, etc. So I'm running out of time. So let's see. Let's calculate this commutator. So I will have to be a bit quick here. So if we have a look, we will use one relation for the epsilon matrices here, namely that epsilon I, j, k, I, l, m. The point is that there is one common index here, I. So this I can, of course, either be 1, it can be 2, or it can be 3. The other two entries here on epsilon, they must be different. So we can have 2, 3 here. For example, let's say that we're interested in the component where we, in this expression when j is 2 and k is 3. Then L and M here can be either, it can also be 2, 3, or it can be 3, 2. But it cannot be anything else because we need to have different indices everywhere. Now, if we have 2, 3 everywhere, then either we have 0 signs from this, well, in this case, if it is 1, 2, 3, we have 0 signs from this guy, and if it is, we have 0 signs from this guy. But in general, when we have the order here and here being the same, depending on if it's, if we take the other guys, the P2 guys here and the P2 guys here, so we call that these are 3 indices, then we have a minus sign from this guy, and we have a minus sign from this guy. So the minus sign will cancel. So if these indices here and here stand in the same order, that is j is equal to L. Now I'm coming here, then I have this guy. And then the other two must be the same. But if they stand in different order, so I have 2, 3 here and 3, 2 here, then I have a minus sign. So I have a minus the term where they stand in opposite order. Now, doing this, and now I know I'm running out of time, but I'd like to do this because I'd like to get to see a first example of what a commutator actually is and how that can be calculated. So we can sort of close the bag and say that we have received some understanding of the algebra, some example of what it can be. Okay. So let's then consider the commutator I, A, I, J. So this is, so I just write out the commutator. So this is matrix I, A, J, components K and L, and then minus I and J swapped, component K, L. Now this is a matrix product, so I write it as a sum over some internal matrix which I'm summing over. So it's I, K, M, and then same M here because the same matrix component, and then that J from there, and that L from there, and the same for this guy, similar structure. Now this IKM is some minus epsilon IKM, and here we have some minus epsilon JML. We do exactly the same thing here. There, in the next place, I just rearrange the indices such that the m's are standing first in both cases. So there is a cyclic rotation of the indices here and here, so that doesn't change any values, and the same here. Then I write out this epsilon product using this equation up here, and I do the same thing for this guy here. Then a few terms turns out to cancel, so I get this expression here, which is again of this form up here. I know it's impossible to follow the details, of course, so I get these epsilon multiplication here, where I'm just swapping the order of a few indices. So Mij, Mij was the same, but MLK, yeah, MKL it is there. So this guy induced that minus sign here. So this is then epsilon IJM from there, and then this minus sign and this guy is grouped into IMKL, MKL. So in other words, this is the KL component of this thing here. So we see that we have arrived at the okay, and this should be clearly be true for all components KL. So we see that we have arrived at this relation for the commutator. The commutator AI and IJ is epsilon IJM AM. And this is then the result for the commutator in this SO2 algebra, and these epsilons here are then the structure constants. And you may also see that this is very familiar to the SU2 case. So we've got our first example of an algebra, and the first examples of the structure constant. Sorry for running over time. Are there any questions to this? So with respect to the lecture notes, I will, as I have mentioned, update them frequently. So I will correct the typos of today. And also I should warn that there's no point in printing the whole document today and using it, because I will change it quite a bit. Okay, so So then let's end the lecture, although I will still stay on for a few minutes to see if someone has some more questions. Otherwise, I see most of you on Tuesday.
I have a question regarding the linearization stuff. If we think about the Lie algebra as a manifold, would this, or as the Lie group as the manifold, would the Lie algebra just be the tangent space?
Yes. Yeah, it would be the tangent space. Exactly.
Okay,
so
cool.
It when you differentiate. But we don't really need it. We don't need to be that fancy with the math.
No, I just noticed because the Lie algebra for SO3 is the same as the tangent space of SO3.
Yeah, it is the same as the tangent space.
Exactly.
Of course, we get it by differentiating, so it is the same thing.
Exactly. So I don't know. I just noticed. I just want to ask if it was the same like all the time, or if it's just a coincidence.
No, it is not a coincidence. It's the same. I think I said so.
Yeah, you did. Thank you.
Okay. Any other questions? So now there's only a few students remaining. Maybe one of you or more of you would like to ask a question. But if there are still no questions appearing, I will end the meeting. Okay. So thanks for today. Bye.